We just saw where we can kind of look at the behavior of a graph and write limit notation that way. We can also do so, sometimes it helps to see it in a tabular form. In fact, the next two lessons are going to focus on us looking at graphs and tables in order to write some limit statements. But let's consider a function here. And it's going to be a piecewise function called g of x. And we're going to have the piece x squared plus 2, which is the parent parabola, the parent quadratic function, a parabola that's been shifted up 2 units. And we're going to let it be x squared plus 2 for all x not equal to 1. And then we're going to let it equal negative 2, specifically at the point for x is equal to 1. And so let's get a graph here, and then we'll construct a table of values to kind of see what's happening. But as I said, it's going to be the parent quadratic function shifted up 2, except at x equals 1. So the left side of my parabola is going to look very normal, but the right side of my parabola here is going to produce a hole at x equals 1, because at x equals 1, and this is just kind of a weird particular piecewise function that I'm looking at, but at x equals 1, I define this as equaling negative 2. And so I end up with this point right here, and there's the graph of my function g of x. Well, we want to describe what's happening to the graph of this function at x equals 1. And so if I build a table, and what I want to be doing here is I want to be getting really close to 1. So I'm going to look at 5 values. And the middle value, I'm going to actually let be x is equal to 1. And I know by definition of my piecewise function here that at x equals 1, g of 1 is equal to negative 2. But for all values not equal to 1, I need to substitute it into this x squared plus 2 piece. So I'm going to look kind of similar to what we did in topic 1.1. I'm going to look at 0.9, and then I'm going to look at 0.99, and then I'm going to look at 1.01 and 1.1. And I'm going to substitute these values in. You can verify them using a calculator, or if you're really good at squaring numbers that are decimals, you can do so as well. But if I take 0.9 and then square it and add 2, that gives me 2.81. If I take 0.99 and square it and then add it to 2, I get 2.9801. 1.01 squared and then added to 2 is going to be 3.0201. And if I do the same thing to 1.1, I get the value 3.21. And so something interesting happens here. Even though g of 1 equals negative 2 by definition of my piecewise function, if I wanted to talk about the limit as x approaches 1 of my function g of x, in other words, as x is getting really close to 1, what are the function values getting close to? And so what ends up happening is I don't even really want to look at this x equals 1 piece. I'm just looking at what's happening around it. Well, as x is getting close to 1, from both directions, it sure looks like my function is getting close to 3. And graphically, that's what's happening as well here. As I'm getting close to 1, and again, I'm not worried about what's happened actually at 1. As I'm getting close to 1, my function is in fact getting really close to the value 3. And we understand what's happening here with this particular quadratic function. If I hadn't made this weird statement at x equals 1, as I get close to 1, the function is getting close to 3. And so the limit as x approaches 1 of g of x is not negative 2, even though this statement is true. The limit as x approaches 1 of this function is 3. And it's a very, very important distinction for you to make, that what's actually happening at the value, in this case, what's actually happening at x equals 1, has no bearing on the limit. We're just looking at the behavior of the graph around x equals 1. And for this particular function, as x is approaching 1, g of x is approaching 3. And so this is the limit statement that I want to be able to write.